In this video, we will describe the framework and the extensive feeder modeling that will enable us to perform the protection coordination under different high PV penetration scenarios. Here are the details of the feeder that we are studying. It's about 9 miles long and has a peak capacity of 13 megawatt, and the peak load that we have seen in the duration of the study is less than 7 megawatt. There are about 3,000 residential customers and about 300 commercial customers. To highlight the complexity involved in the extensive feeder modeling, the primary itself has about 2,000 segments, and then we are modeling the secondaries, which has another 3,000 segments. There are close to 1,000 transformers, 3 capacitor banks for voltage control, and there are about 186 lateral fuses, in addition to all the fuses on the primary of the transformers. There are also 2 reclosers. The reclosers are shown by these red circles. There's one mainline recloser, another recloser for this main lateral. And of course, the substation has this relay. And in this base feeder, we have added a high PV penetration, and the residential PV, the rooftop PV, there are about 125 systems, which total about 467 kilowatt. These are 2 to 4 kilowatt system. And in addition, there are also 2 large-scale PV systems, one at the Dhoni Park rated about 600 kilowatt, and another one on a school rated at about 470 kilowatt. So on a feeder of less than 7 megawatt load, we have a PV of about 1.5 megawatt, and at light loads you have seen penetrations as high as 40%. This study also has extensive data acquisition systems. We have 7 weather stations and 6 high bandwidth DAS spread along the feeder. And in addition, there are also 17 residential DAS on 17 of these 125 residential PV systems. And all the loads, and as well as all the PVs, they have their own AMI. The DAS may not be very significant just for the protection part of the study, but we use these feeder DAS and the residential DAS extensively to completely validate the models that we get with the field measurements, so that we have a very high confidence in the model that we developed, and we use that model for the protection coordination study. For the protection itself, it is these 3 parameters that is most relevant: the large number of lateral fuses, the 2 reclosers, and the substation relay. And we will be studying the coordination among each of these devices for different types of faults for different PV scenarios. Here I present an overview of the modeling process. The first step in modeling is to gather the very extensive GIS data available. So the GIS has the information on all the line and equipment in the feeder, and it has the basic location information, the IDs, and all the physical attributes. And for each of the line and equipment listed in the GIS, we need to collect all the electrical characteristics, like the line type, the conductors, the number of strands, and so on, which come from various standards. For transformers, for example, we need the impedances, the X/R ratios, and so on. So the data, electrical data for all the equipment, need to be collected. Then we need the load data, and that comes from the measured AMI data in 15 or 1 hour intervals. And we also need the PV output data, which also comes from the measured AMI data. And we also need, for the complete modeling, the ratings of the inverters, and obviously the location and the IDs of the PV generators. So in addition to the AMI data, sometimes we also make use of the feeder DAS and the residential PV DAS measurements to obtain some finer resolution data than what is generally available from AMI. MATLAB is the main engine that we use to form the feeder model, starting from the GIS information and all the equipment load and PV data. There are three main steps involved. Probably the most involved step is the topology identification. So this is where we develop the complete electrical network model, basically the one-line diagram of the feeder. Then we need to add all the equipment to this network, and also add the load and PV, map them to the same feeder network. OpenDSS is the distribution analysis tool that we use in this study. So MATLAB at the end of these steps creates all the files that OpenDSS needs to run the powerful analysis, the snapshot, the time series analysis, or the harmonic analysis. So in addition to creating these scripts, the files that OpenDSS needs, MATLAB also commands the OpenDSS through the COM interface, especially to do time series analysis kind of simulations. So OpenDSS is used to run multiple power flow and time series analysis to study, for example, the impact of different PV levels on the voltage profile of the feeder, or the losses in the feeder, and so on. Now these results are also used in comparison with the measured DAS data under similar scenarios, and together they are used to validate the model that we developed. And if there are discrepancies, that gives a feedback to the MATLAB engine to make adjustments to refine the model, so that the analysis results completely match with the field measurements. So through this validation, we have a very accurate feeder model on which we can have a high level of confidence. So once we have this, then we can use this model for the protection analysis. Once again, MATLAB is the main analysis engine that we use for the protection study as well. So in this part, the MATLAB determines all the fault cases that we need to run for a specific coordination analysis, say fuse to recloser. We determine all the fault cases that need to be applied through MATLAB, and MATLAB commands the OpenDSS through the COM interface to run each of these fault cases, and from the OpenDSS model, then we get the corresponding fault currents, which is input to the MATLAB, and MATLAB compares these fault currents with the protection device TCC curves, time current characteristics, and the currently used settings. And by comparing these with the measured fault currents for the different fault scenarios, MATLAB can determine whether or not the coordination is maintained or is violated. And the same scripts can also be used to come up with a complete design of the various protection settings for different PV penetration levels. Briefly, the equipment modeling, conductor modeling in this slide. There were a total of 39 line types in the primary of the Sandvik feeder, some overhead, some underground. In addition, there were several secondary line types as well, and they have been modeled as the corresponding triplex conductor types in OpenDSS. So for each of these line types, the corresponding models, including the diameter, number of strands, resistance, GMR, and so on, which were obtained from various standards and handbooks, and they were used to create the library of the various line conductor types. The level of detail included looking at the specific framing methods used in this flagstaff feeder, clean versus cross-arm construction, and that was also included in the library of the conductor. So this information was used in SIMDIST, another distribution analysis software tool, to get the corresponding positive and zero sequence impedance of the various conductor types. So here is a list of the impedances, positive and zero sequence impedances for all the overhead lines as an example. and this was obtained from SIMDIS. It was also verified by a hand calculation using textbook equations, and a conductor data report was compiled for all the conductor types on the Sandvik feeder, and that has been vetted by the project partners. Regarding the transformer, there are several single-phase and three-phase transformers, and for each of the transformers, the corresponding electrical parameters, mainly the impedance, the X and R, and the X over R ratio for both three-phase and the single-phase transformers were obtained. As you can see, for the single-phase transformers with very low kVA, the X over R ratio is very small, typical of low power distribution transformers. The main substation transformer was also modeled using its positive and zero sequence impedance, looking from the low voltage side into the sub-transmission system. This is the flow chart of the process to develop the complete feeder network model starting from the GIS data. So the first step obviously is to read the GIS data, which is normally given in the MDB file or the GDB file format, both of which cannot be read by MATLAB. So the first step is to convert the MDB file into shape files which the MATLAB can read. The next step is the topology identification. This is the process of finding the electrical connection of the line segments and the equipment. The GIS data only indicates the locations of the lines and equipment and does not provide explicit information about the how the line segments are electrically connected to one another. So we need to perform this iterative algorithm for topology identification. So essentially, at the end of this process, we should have a complete list of all the nodes or the buses in the feeder and all the sections or branches connecting these various nodes, with each section having an unique from node and to node. So that completes the that gives us the complete electrical connection of the different nodes. So after finding all the nodes and sections, the next concern is to determine whether the identified topology is a single fully connected network. So to do that, we need to go through this island analysis algorithm and make sure that the topology is a single fully connected electrical network and no small islands exist. Now, if there are islands, then we need to relook at all the switch positions. The next step is to link all the lines and cables in the feeder to their line type and cable type that we defined in the conductor library that I described in the previous slides. Similarly, all the other equipment like the transformer, switches and shunt caps are also associated to their respective equipment library. So after all of these steps, we have the full model in MATLAB. So the next step is to write the corresponding text files in a format suitable for either OpenDSS or SIMDIS, so that we can run power flow analysis in those tools. Then the PV generators. So all the 125 rooftop PV systems as well as the 2 large PV systems, they are modeled as the distributed generators. So OpenDSS supports that, and SIMDIS also models them as electronically coupled generators. As described earlier, we have an automated process to associate PV with their correct endpoints and create a PV section for the individual generators. The active power output of the PV is set equal to the measured data for each of them, and where measured data is not available, it is estimated using data from other inverters and weather station data. what is important for the protection analysis here is the fault current contribution, and that is presently set at 200% of the inverter's rated current, and it is assumed to be in phase with the terminal voltage, and it is assumed to persist at a constant value for the entire duration of the fault. Now, this is the assumption that we're using, and this can be refined as we get more accurate data from the inverter manufacturers.